Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be going through material from Math 136 for your online class at Ivy Tech. We're going to start with section 5.1, which is all about polynomial functions and models. So the very first thing that we need to learn how to do is to actually identify a polynomial function as well as something called its degree. So a polynomial function is always going to look something like this. You're going to have f of x or y equals, and then you're going to have some number, okay, and we're just going to call it a sub n times x to the n power. Now, an minus 1, a1, and a0 are all going to be real numbers, and n is going to be a non-negative integer. So basically what we're going to have is some combination of numbers times x's to some power that are positive powers, okay? And then the domain of polynomials is going to be the set of all real numbers. So we want to just take a look at these and decide if these are polynomial functions or not. And then for those that are, we want to go ahead and state the degree. And then those that aren't, we want to tell why not. So if we look at question A here, we have f of x equals 3x minus 4x cubed plus x to the 8th. Now, so this has x to positive powers. We have the 8th power, the 3rd power, and the 1st power. And we have nice numbers here, 3, 4, and 1. So this is a polynomial, and the degree is always going to be the highest power that's attached to x. So if you look at this, the highest power that we have attached to an x is the 8th power. Okay, so that means that the degree is 8. If we look at b here, we have g of x equals x squared plus 3 over x minus 1. And this one is not going to be a polynomial function because it's the ratio of two distinct polynomials. So we can't have division here because of the fact that x minus 1 does not go nicely into x squared plus 3. If this were divisible, then we'd be able to deal with it, but this one in particular is not going to work because it's two distinct polynomials. The numerator is a polynomial, the denominator is a polynomial, but together they're not a polynomial. This is a rational function. If you look at C, we have h of x equals 5. This is going to be a polynomial, and the degree is going to be 0, because if you think about it, x to the 0 power is just going to be 1. Okay, so we could rewrite this as 5 times x to the 0 power, which would still just be 5, so we wouldn't have changed it all, but then the degree is going to be 0. So you can see that we don't actually even need x's in our polynomial function because we have this number here. We could also have a 0 or a 1 there, and it would still be a polynomial function. Anytime you just have one number, though, the degree is going to be 0. This one here, we have f of x equals x minus 3 times x plus 2. This isn't written in the way that we're used to seeing, but this one's fine. So if we were to FOIL this out, we would get x squared minus 3x plus 2x for the first outer inner, and then we'd get minus 6 for the last terms. And if we combine like terms, we would end up with this right here. F of x equals x squared minus x minus 6. So if you look at this, the polynomial is going to have a degree of 2 because 2 is the highest power that's attached to x. It's important that you look at this in the written out version, okay, so the expanded form, because otherwise it's a little more difficult to see the degree. Now, it is possible to look at the original and see the degree as well. We could look and say we have an x here, and then we have another x here, so that gives us a degree of 2, and that's fine to think about it that way as well, or you can multiply it out to see it really clearly. Now e right here, we have g of x equals 3x minus 4x to the negative first power. So for this one, if you notice, we have this issue here where we have x to the negative first power. This one is not going to be a polynomial function because this second term does not have a non-negative integer exponent. So we have to have some exponent that's either 0 or positive, and an integer. So this one just isn't going to work. And if we take a look at h of x, we have h of x equals 1/2 times x cubed minus 2/3 times x squared plus 1/4 times x. Now you'll notice we don't have as nice of numbers out in front here, but it doesn't matter. Okay, this is still going to be a polynomial. We just have fractions. That's no big deal because the fractions just have numbers in them. We don't have a fraction that has an x in the denominator, which causes an issue. And our powers are very nice. We have x cubed, x squared, and x to the first. So the polynomial is going to be a degree of 3 because that is our highest power. So here's a nice little summary of some of the properties of the graphs of polynomials. So if you have something where you have f of x equals 0, this is still a polynomial, but this one is actually called the zero function. It has kind of a special name, and we say that it has no degree. Okay, that's kind of the only one that's like that. And the graph is just the x-axis. Now, if we have something where we have f of x equals a sub 0, where a sub 0 is not 0, so something like f of x equals 5, like we had on the last slide, or f of x equals 2, then the degree of the polynomial is 0, and it's a constant function. So if you think of what the graph is going to look like, if you have y equals 2, for example, as your function, it's going to have degree of 0, it's going to be a constant function, and it's just going to be a horizontal line that has the y-intercept at that point. So if we had y equals 2, it would just be a horizontal line going through 0, 2. Now you can also have something of degree 1, where we have f of x equals a sub 1 times x plus a sub 0, where a sub 1 is not equal to 0. Okay, a 0 could be 0 though. You don't need a number there. So basically where you just have one x term and it's raised to the first power. This is going to be a linear function, okay, and we've talked about linear functions in this class before. a1 is going to be the slope and a0 is going to be the y-intercept. And then you've also seen this before. This is a quadratic function. So if you have a degree of 2, meaning that you have x squared as one part of your equation, then you're going to have a quadratic function, which, if you recall, looks like kind of a U shape. It's a parabola. The graph is going to open up if a sub 2 is greater than 0, and it's going to open down if a sub 2 is less than 0. So if we look at these pictures right here, we can also look at graphs and determine if they could be a polynomial function. And if we look at this graph for A, it's nice and smooth and continuous, okay? There aren't any corners or cusps like we have over here, or holes or gaps. There's nothing like that. So the graph is going to just be nice and smooth and continuous, okay? But over here, this cannot be the graph of a polynomial function because of several reasons. There's a corner right here, okay, it makes kind of a sharp turn. We also have this thing called a cusp right here, okay, a gap, which means that we have kind of a hole in one place and then a solid point in the other, and then we have a hole over here. Okay, so these are the kinds of things, we're going to talk about holes a little bit later, but these are the kinds of things that you might see maybe if you have a rational function, even if something cancels, okay, from your numerator and your denominator, and it looks like it might be a polynomial. Because it canceled, you're going to end up with a hole there, which we're going to talk about in a little bit, so that still cannot be a polynomial function. So anytime you have x's in your denominator, you're not going to have something that is a polynomial. Okay, the next thing we want to talk about is power functions. Okay, so a power function of degree n just looks something like this, where we have f of x equals a times x to the n. A is going to be a real number, not equal to 0, and n is going to be an integer that's greater than 0. So some different power functions could look like this. We could have f of x equals 3 times x. This would just be degree 1. F of x equals negative 5x squared. That's a degree 2 power function. F of x equals 8x cubed. That's degree 3. And f of x equals negative 5x to the fourth. That's degree 4. So all of these, you could have a different number out front, okay? But the power that's attached to your x is still your degree. So if we take a look at these graphs right here, we have the ability to kind of see what some of these might look like, okay? So if we have f of x equals x to the 8th power, x to the 20th power, and x to the 40th power, what you're going to see is that as we put in small numbers for x, so x equals 0.1, 0.3, and 0.5, you'll notice that as the power gets larger, the actual y value gets smaller, okay? And if we look at this graph right here, the black graph that's shown on the left is y equals x squared. And then the blue graph that's shown, if you notice, it's a little bit flatter towards the origin, okay? But it rises a little more quickly in the middle. So this would be the graph of something where you have f of x equals x to the n power, where n is greater than or equal to 4 and n is even. So this might be the graph of f of x equals x to the 4th, or x to the 6th, or x to the 8th, some even power that's larger than 2. And then we can even compare x to the 4th, which is shown now in black on the right, so y equals x to the 4th, with y equals x to the 8th. And what you'll notice is, again, it's a little flatter towards the origin, but it grows more quickly. Okay, the larger the power, the more pronounced this is going to be. So the more quickly it will grow, the flatter it will be towards the origin. So there are some nice properties of power functions. If you have an even positive integer, so the first property is that if you have this positive even integer and you have a power function, f is going to be an even function, which means that its graph is symmetric with respect to the y-axis. Domain is going to be the set of all real numbers, and the range is going to be the set of non-negative real numbers. And then these points, these 3 points right here, are always going to be on the graph. So -1, 1, 0, 0, and 1, 1 are always going to be on the graph no matter what. And then as the exponent n increases in magnitude, the function increases more rapidly, but for x's near the origin, it tends to flatten out and lie closer to the x-axis, which is exactly what we saw on the previous slide. Now we also want to look at odd functions, okay, so hopefully you recognize this black graph on the left, which is y equals x cubed. That was one of our functions that we should have learned a few sections back. And then if you look at the blue graph that's kind of next to it, you'll notice again that this blue graph is flatter towards the origin, okay, so it's a little bit flatter, and it grows more quickly everywhere else. So this is kind of the same thing over here. Y equals x to the 5th is shown in black, and then y equals x to the 9th is shown in blue. And it has very similar properties as the positive even integer power function, but this one's odd. So obviously first it's not going to be an even function, it's going to be an odd function, which means that it's symmetric with respect to the origin. The domain and the range in this case are going to be the set of all real numbers. There are 3 points again that are contained. They're different points than the last one, but we have points -1, -1, 0, 0, and 1, 1. These 2 points are the same as the last one. And then the behavior kind of stays the same. So as the exponent increases, the function increases more rapidly, except near the origin where it tends to flatten out and lie closer to the x-axis. So this is the exact same behavior as our even power function. So we can graph polynomial functions using some transformations. So if we have something like this, let's say we have f of x equals 1 minus x to the 5th. Hopefully you remember some of the things we've already learned about transformations, but if we take a look at this blue graph right here, since we have the 5th power, that's an odd power, so it means that it's going to pretty much look just like y equals x cubed, except it's going to be a little flatter near the origin and it's going to grow a little more quickly. But we don't care about that so much, we just kind of want these 3 points, which gives us a nice smooth curve, and then we're going to do some transformations with it. So since we are multiplying by -1 because we have this negative out front, that means we're going to reflect our graph around our x-axis because we have our negative in front of our x. So I just take this graph, this blue one right here, and I flip it around my x-axis, and I end up with one that is basically just an upside-down version of the original. And then the last piece of the transformation is to deal with this 1 right here. So since we add 1, that means that we just take our graph and we shift it up 1 unit. So it just looks like something like this. So we take our graph from the second step and then we just move it up by 1. And that gives us our nice transformed graph. Now the more typical way to write this would be y equals -x to the 5th plus 1, but they kind of rearranged things when they wrote it. It's written here as 1 minus x to the 5th, but this is the exact same thing, just rearranged. All right, let's take a look at this one. Let's say we have f of x equals 1/2 times x minus 1 to the 4th. So for this one, we kind of need to figure out what our base graph is going to look like. So what you're looking for is you're looking for the power that's attached to x. So in this case, we have x to the 4th power. Now, hopefully you remember when you have even numbers, okay, x squared, x to the 4th, x to the 6th, things like that, you're going to have this parabola shape, okay, right here. So it's going to look something like this. We have these 3 points again, -1, 1, 0, 0, and 1, 1. This one is a little flatter than x squared, and it grows a little more quickly. Now, if you notice, we have this minus 1. This is kind of inside of our function. So our x has been replaced by x minus 1. And hopefully you remember from transformations. If you're confused on this, I would make sure you go back and watch the video that we talked about with transformations, which I think is from chapter 3. You're going to take this x, replace it with x minus 1. That means that we shift our graph to the right by 1. Okay, this is the one that I like to say is kind of counterintuitive because we have the negative, but it's actually shifting it to the right 1. So we take our nice blue graph over here and we just scoot it to the right 1. And then the only thing that's left to do is multiply by 1/2, which is going to be a compression by a factor of 1/2. So our graph actually gets a little wider. All of our y's are halved. Okay, so instead of going through 0, 1, it goes through 0, 1/2. Instead of going through 2, 1, it goes through 2, 1/2. The 1, 0 stays the same because half of 0 is still just 0. So this would be our final graph right here. Okay, the next objective is to be able to identify the real zeros of a polynomial function along with something called the multiplicity. Okay, so this is kind of a confusing word, but it's not actually that difficult once you get into it. So let's look at this right here. So let's go through this definition. If f is going to be a function and r is a real number for which f of r equals 0, then r is called a real zero of f. Okay, and then as a consequence, the following statements are all equivalent. Okay, so we can say that r is a real zero. We can say that r is an x-intercept. So x-intercepts and real zeros are going to be the same thing. We can also say that x minus r is going to be a factor, and that r is a solution of the equation f of x equals 0. So let's take a look at what some of this means in practice. So let's say we have a polynomial. We know the degree is 3, and we know that we have these zeros here of -4, -2, and +3. Okay, so we're not given the polynomial. We have to actually find it. So if you think about this for a minute, if we know that -4 is a 0, that means that x plus 4 has to be a factor. So this x plus 4 is here because -4 is 0. So if you think about it, if you take -4 and you plug it in for x, what's going to happen is you're going to get -4 plus 4, which becomes 0, and it just wipes out this entire side of this equation. It just makes it 0. So that one definitely works. If we have -2 as a 0, that means x plus 2 is going to be a factor. Again, if we check it by kind of plugging it in, if we plug -2 in for x, we're going to get a 0 here, which again, 0 times anything, it's just going to multiply out and just become 0 on this entire side, just like we'd like. And if we have +3 as a 0, that means that x minus 3 is going to be a factor. Again, if we check it by plugging a 3 in, 3 minus 3, that's just going to give you 0, which is again going to knock out this entire side, just make it 0. Now you'll see we have an a out front here. This can kind of be any number that we'd like it to be, okay? The easiest thing to probably do is to just let a equal 1, okay? So in this case, we just plug 1 in for a, and that would be our final solution. Now make sure that you pay attention in my math lab. They may want the factored version, which is going to be this original one, but with just a number 1 out here or no number at all. Or they may want the expanded version, which is the one that's given down below here. And in order to get this, you just have to FOIL the first two and then take that and distribute the x and the -3 to everything and combine like terms. So it's basically foiling and then distributing. Okay, so you will have to do that if you're asked for the expanded version. But if they just want the factored version, then you can just type in this first one here. But instead of actually typing an a, you would just put any number out there that you'd like. You could put a 2 out front, you could put nothing at all, which would just be a 1. It doesn't really matter too much. Okay, so now let's do this the other way around. Let's take a given polynomial and then identify the zeros along with their multiplicities. Okay, so what we want to do is we want to look at our polynomial piece by piece. Okay, so if we look at this, we know that we have x minus 2 here. That means that 2, +2, is going to be a 0. Okay, so the reason for that is because if we plug a +2 in for x, we get 2 minus 2, which makes this 0. Okay, so this is going to be a 0 of 2. Now the multiplicity is really just the power that's attached to this factor. So if we look at x minus 2, we have x minus 2, and then the power that's out here is just the first power. So that means that we have a multiplicity of 1. So we have a 0 of 2 that goes with a multiplicity of 1. Now I want you guys to take a second. Let me give you about 15 seconds to see if you can figure out what these other two zeros and their multiplicities are. Okay, so hopefully you were able to figure out that -1 is going to be the 0 that goes with this factor, and then the multiplicity is going to be 3 because that's the power that's attached. And then for the last one, you're going to have a positive 3 as the 0 for this one, because if you plug positive 3 in, it makes this factor 0. And then the multiplicity is going to be 4 because that's the power that's attached to this factor. Okay, so let's take a look at how to graph a polynomial using its x-intercepts. Okay, so if we have this polynomial here, f of x equals x times x minus 3 squared, we want to find the x and y intercepts, and then we're going to use them in order to kind of create intervals and decide if our graph should be above or below, locate a couple of other points, and then draw a nice smooth curve. So if we want to find the x-intercepts, hopefully you remember you have to set y equal to 0. Okay, so I put a 0 here. I have 0 equals x times x minus 3 squared. And if you use our zero product property that we learned before, you would find that you get x equals 0 as one of the zeros, and you'd get x equals 3 as the other 0. So these are our two x-intercepts. To find our y-intercept, we just plug 0 in for x. And we should just get 0 out for y because that was one of our x-intercepts as well. So y equals 0 is our y-intercept. So if we take a look at a number line here, we have a number line, it has a 0 on it and a 3 on it because those were our two x-intercepts, 0, 0, and 3, 0. And then we write these as intervals. So this interval is going to go all the way from negative infinity up to 0. And then we're going to have another interval from 0 up to 3. And then a third interval from 3 to infinity. And then all we need to do is just plug in some points, okay? So we just pick a nice number that's in this interval. -1 is pretty nice. And when we actually take -1 and we plug it into our equation, we get -1 times -1 minus 3 squared, which is going to give us -16. So that means that on the graph, it's going to be below the x-axis because it's a negative number. And the actual point is going to be -1, -16. And then we just do this for each. So we're going to pick 1. So we're going to plug 1 into our original equation. So we have 1 times 1 minus 3 squared. You can use a calculator to do this. And you should get 4 out. 4 is a positive number, so that's going to be above your x-axis. And if we write it as a point, it's going to be 1, 4. And then let me give you guys a minute to try this one. So you're going to plug 4 in, you're going to decide where that's going to be, and you're going to write it as a point. So let me give you a minute to go ahead and do that. Okay, so when you plug 4 into your original equation, you should get 4 out, okay, because you just have 4 times 4 minus 3 squared. 4 is a positive number, so it's going to be above your x-axis, and the point on the graph is just going to be 4, 4. So if we take a look at an actual graph of this, we're going to use all this information that we have down here. We know that we have an intercept at 0, 0, and 3, 0, so we plot those first. And then we're also going to have some points. We're going to have a point at -1, -16, which would be way down here, but you can see that it looks something like this because it's going to be below our axis. We also have a point at 1, 4 that we had found, so that's going to be kind of this top point here, all right? And we don't exactly know how high up this goes, but that doesn't matter too much. And then we also have a point at 4, 4, which is going to be right here, and then it's going to continue on. So you can see that from negative infinity all the way up to 0, we're below our x-axis. And then from 0 to 3, we're above our x-axis, and also from 3 to infinity, we're above our x-axis, which matches with what we determined down here. Okay, now the important thing, the reason that we actually list multiplicity is so that we can figure out if our graph touches or crosses at certain points. So anytime you have a multiplicity that's even, it means that your graph is going to actually touch there, okay? And the way that I tell my students to remember this is just remember the movie E.T., okay? So even goes with touches, E.T., and then if you have something that's odd, that means that it crosses, okay? And I don't have a nice little thing for this one, but if you remember ET, even touches, then you'll also remember that odd crosses because it's just the opposite. We're also going to talk about behavior near a zero, okay? And this is not as important in identifying graphs, but you may be asked to find this kind of in the larger picture as just one of kind of the small pieces that you can do to help you get your final graph. So let's say that we have f of x equals x squared times x minus 2. And what we want to know is what the behavior of our graph looks like near the 0, 0, okay? So in order to do that, what we do is we actually substitute 0 in for x, except for the part of the equation that 0 came from. So if we're using the 0, 0, okay, that means that we're looking at this part right here. So that's where 0 came from. So all we need to do is we need to just plug in 0 for x everywhere else. So all we do is we just keep x squared, we leave it alone, okay, because if we plugged 0 in there, it would just make the whole thing 0, which would not be helpful. And then we plug 0 in for x for our other x, so we get 0 minus 2. And if we simplify this, we get negative 2x squared. And if we actually take a look at this near 0, we'll find that our graph looks kind of like an upside down parabola, just like negative 2x squared does. Okay, so that's what that one implies. And we can look at the actual points here as well, but I don't think it's really so important that we do that. What you can see is that if we actually look at these points, it does indeed near 0 look like this upside down parabola of negative 2x squared. Let's take a look at this one right here. So if we want to know what the behavior looks like near the other 0 for 2, okay, so if we go back one slide, 2 is going to be our other 0 because when we plug 2 in, we get 0 for this factor, which makes the entire thing 0. So if we plug 2 in, we don't want to plug it into the second piece this time because if we plug it in there, it makes our function 0, which we don't want to have happen, okay? So we just substitute 2 in everywhere else. So if we do that, we have 2 squared times x minus 2, which is just going to be 4 times x minus 2, which just looks like a line that has a positive slope and a negative y-intercept. And again, if we look at this near this 0, if we look at 2, it's going to look pretty much just like a line there. And you can see it on this graph here. We have kind of this line, this linear shape here versus a parabola that we had over here. Okay, so the multiplicity actually determines whether the graph is going to cross or touch the x-axis at a 0. Again, remember ET, even touches. And then the behavior of the graph near a real 0 determines how the graph crosses or touches. Okay, so it can look a little different based on what the graph near the real 0 looks like. So this one behaves like a line, this one behaves like an upside down parabola. Now the next theorem, and we're going to put this all together in just a minute, but we're going to go through all of these kind of little pieces and then we're going to put them together to create one nice graph. This theorem though is about turning points, okay? So if f is a polynomial function of the degree n, then f has at most n minus 1 turning points, okay? And then if a graph of a polynomial function has n minus 1 turning points, then the degree has to be at least n. So if we have f of x equals x minus 1 to the 4th, then we know that the degree is 4, so that means that we have at most 4 minus 1, which is going to be 3 turning points. And then n behavior is kind of the other important thing. So we talked about power functions before. All you have to do to figure out the n behavior is identify the power function of your polynomial, and then whatever the end of that graph looks like, that's what the end of your polynomial is going to look like. And in order to figure out the power function, all you do is you just rearrange your polynomial so it's in descending power order so that you have the largest power first and the smallest one last, and then your power function is just the first piece that you have right here. So if we look at this right here, we have a couple of different end behaviors that we can go through, okay? So if you have something where you have a power function where n is greater than or equal to 2 and even, okay? So if you have some kind of power function where you have an even positive number, then you know that your graph is going to go up on the left and up on the right. And something is going to happen in the middle, and we'll use our other techniques to figure that out, but we know it's going to go up on the left, up on the right. And then in addition, if you have some negative number and you have an even power, okay, so an even power still, but this time you have a negative number out front in front of your x, that means that it's going to make your graph open down on both sides. So on the left it goes down, on the right it goes down. Now for odd, if you have something like x cubed or x to the fifth, something like that, you know it's going to go down on the left and up on the right, and then something's going to happen in the middle here. But if you have something where you have negative x cubed or negative x to the fifth, where you have some negative number out front, then it's going to flip-flop. It's going to go up on the left and down on the right. So if we look at this graph right here, we can determine which one could possibly be our graph. So if we have f of x equals x to the fourth plus 5x cubed plus 5x squared minus 5x minus 6, what we can go ahead and do is we can find our our y-intercept pretty easily. So if we plug 0 in for all of our x's, we're just left with -6, which is going to be our y-intercept. And if you look at the actual graphs, this one has a negative y-intercept, this one has a negative y-intercept, and this one has a negative y-intercept. But graph A definitely has a positive y-intercept, so that one is certainly not going to work, so we can cross that one out. We know that the degree is 4, okay, because we have a highest power of 4. So that means that the maximum number of turning points is going to be 4 minus 1, which just gives us 3, okay? So the maximum number of turning points is 3. And if you look at our graph, we have a turning point 1, 2, 3. That one's okay. This one, though, we have a turning point 1, 2, 3, 4, 5 turning points. So C is not going to work. So we can cross that out. And D has 1, 2, 3 turning points, so that one is okay as well. Now the big difference between B and D is that one is opening up on both sides, the other one is opening down. So what we need to think about is what our power function is. And recall, if you have something where your polynomial is written in descending order, then your power function is going to be this first term. Okay, so our power function is just x to the fourth. And if you think of what the graph of x to the fourth actually looks like, it's just going to be kind of a correctly oriented, so it's going to open up, it's going to be a parabola. So that means that we have both ends are going to approach infinity. Okay, so you're going to be opening upward over here. So that means that B looks pretty good, but D, where it's opening down, that one is not going to work. So it has to be B. So here's a nice little summary of how to graph a polynomial function. The degree is going to be n. Graphs are always smooth and continuous. We have at most n minus 1 turning points. If you have an even multiplicity for a 0, then your graph touches there. If you have an odd multiplicity, then it crosses. And then between the zeros, the graph is either above or below the x-axis, which you can figure out by plugging in some test points. And then the end behavior is determined by the power function. So let's look at this right here. Let's say we have f of x equals 2x plus 1 times x minus 3 squared. So the first step we want to take is determine the end behavior. So we want to go ahead and maybe expand this. All right, now I'll leave this to you guys to actually do, but if you square the x minus 3, you get this, and then you would have to distribute the 2x and the 1 and combine like terms. So you should get 2x cubed minus 11x squared plus 12x plus 9. Now this is going to be a degree of 3, so that means that your graph is going to behave something like y equals 2x cubed for large values of x. So if you recall what 2x cubed looks like, I would just keep this in your mind so you have it. It's going to be kind of this shape right here where it goes down on the left and up on the right. And then you want to find the x and the y-intercepts. Now, if you plug 0 in for x, you're going to get 9 out for y, so that's going to be your y-intercept. And then to find the x-intercepts, we have to set y equal to 0. We probably want to use our nice factored version here. So we have 2x plus 1 times x minus 3 squared equals 0. set each piece equal to 0. So we get x equals -1/2, x equals 3. Those are going to be our x-intercepts. And then we want to determine the multiplicity of these. So if we look at the -1/2, that comes from this piece right here. The multiplicity on that is 1. Okay, 1 is an odd number, so that means that our graph is going to cross there because it's odd. And then at 3, the 0 of 3, that comes from this piece right here. That has a multiplicity of 2. 2 is an even number, and hopefully remember ET. Even numbers mean that the graph touches there. Now the maximum number of turning points, the degree we know is 3, okay? So the maximum number of turning points that you have, you just subtract 1, which gives you 2 times. So the most number of times that your graph can turn is 2. And then we want to determine the behavior of the graph near the x-intercept. I'm going to skip this part because it's not the most important piece, and I want to make sure we get through rational functions as well today. But if we put all this information together, the first thing I suggest doing is plotting all of your intercepts. Okay, so you're going to have a point here at -1/2, one at 3, and then a y-intercept at 0, 9. Okay. And then what I recommend doing is drawing your end behavior. So from this x-intercept, we know that it's going to go down on the left and up on the right. We had talked about end behavior just a couple slides back. And then we have to figure out just how to connect basically these lines here. So if you look, we know that at -1/2, our graph should actually cross because this one had an odd multiplicity. So that means that I'm going to go through my x-axis. Okay, it's going to cross my x-axis and it's going to hit this y-intercept. It's going to come back around so it can hit this. And then at 3, it just touches. Okay, so that means that it hits it, it touches, and it goes right back up. So it's just going to look something like this. And again, you can also pick some extra points just to get a nice smooth curve. It looks like they found a point at -1, -16, and 1, 12 as well. So you can see, oh, and 4, 9. So you can see just a little bit more what this looks like and make sure that you didn't mess up any of the steps. Okay, section 5.2 is about properties of rational functions. So a rational function is just a function that's in the following form, and we had kind of talked about this. P of x is a polynomial, q of x is also a polynomial, but not the 0 polynomial. So a rational function is just where you have two polynomials, one divided by the other. Now the domain is going to be the set of all real numbers except the numbers where the denominator is 0. So we've already found domains for things like this, so this should be review here. But if we look at this, 2x squared minus 4 over x plus 5, we should see that x plus 5 cannot equal 0, which means that x cannot equal -5. So the domain is going to be all x's such that x is not equal to -5. If we take a look at this one right here, r of x equals 1 over x squared minus 4. If we take x squared minus 4 and we set it not equal to 0, we're going to get x not equal to -2 and +2. This is because it factors. It's the difference of two perfect squares. So we get x such that x is not equal to -2 or +2. Now if we have something like this, x cubed over x squared plus 1, that's just going to be, all real numbers, because if you try setting x squared plus 1 not equal to 0, you're not going to get any solutions, okay? You would only get imaginary solutions. So for that one, we don't run into any issues. This one right here, we have x squared minus 1 over x minus 1. Now this is kind of one of the ones I was talking about where it might look like it cancels, but we still have to find domain before we actually cancel anything, okay? So if you have r of x equals x squared minus 1 over x minus 1, then what you can do is just say that it's going to be the set of all real numbers except x equals 1. So this numerator, it would factor into x plus 1 times x minus 1, but you don't cancel it yet, okay? So it's important that you find the domain before you actually cancel anything. And that's what's kind of mentioned down here. Although this reduces to x plus 1, it's important to observe that this function and this function right here, although this one is a polynomial and this one is not, they're not actually equal because the domains are slightly different, okay? So this one looks like it could be a polynomial because it cancels and changes into this, but the domains are slightly different from one another. So let's look at this graph here, h of x equals 1 over x squared. So if we want to graph this, we can just plug in some points. Okay, if we plug 1/2 in, we get 4 out. If we plug 2 in, we get 1/4 out, and so on. And it looks something like this. Okay, so we have these two kind of U shapes on either side. And then we can also use transformations in order to graph something that kind of looks like that original, except it's a little bit transformed. So if we have r of x equals 1 over x minus 2 squared plus 1, then we should just identify the original graph here, which is just going to be y equals 1 over x squared, which just looks like it has kind of this U shape here, U shape over here. And then if we look, we have this inside transformation. So x was replaced with x minus 2, which means that we actually shift our graph to the right 2. And you'll notice we have this dotted line. This is called an asymptote, as it has been shifted along with our graph. We're going to talk about how to find asymptotes in just a minute here. And then we've also added 1, which means that we've shifted this up 1. And now you see that we have a horizontal and a vertical asymptote. The asymptotes were originally just along the y and the x axes, and they've moved when we shifted our graph. Okay, so we have some definitions for horizontal asymptotes and vertical asymptotes. And kind of the easiest way to look at this is to look at an example here where we have y equals r of x. Y equals L is going to be your horizontal asymptote, as you can kind of see this blue line is going to actually approach this dotted pink line. So as x approaches negative infinity or infinity, the values of r are going to approach some fixed number L, and that's going to be your horizontal asymptote. If you're going on to calculus, you'll talk about this. This is going to be your limit, okay? And then we also have sort of something that could look a little bit different maybe, where we still have y equals L, but it's approaching it on the negative infinity side. We also have vertical asymptotes, okay? And that means that as x approaches some number c, the values are going to approach infinity, okay? Or they could also approach negative infinity. So you can see that this is kind of the same thing, except we're approaching negative infinity and positive infinity. We can also have oblique asymptotes, which are going to be kind of slanted lines, okay? And we can approach those as well. So if we want to find the vertical asymptote, all we need to do is just make sure that we reduce our function, put it in lowest terms, and then all we have to do is find the real zeros of the denominator. So you set the denominator equal to 0, and that's going to give you your vertical asymptotes. So if we look at this right here, r of x equals 5x squared over 3 plus x. All we have to do is set 3 plus x equal to 0 and solve for x. We get x equals negative 3. That is going to be your vertical asymptote. If we have this one right here, we have h of x equals x minus 3 over x plus 2 times x minus 2. We set our denominator equal to 0, and we just get x equals 2 and x equals negative 2 from each of these pieces. And if we look at one more here, we have f of x equals x minus 1 over x squared plus 5x plus 4. We need to go ahead and factor this. This would factor into x plus 4 times x plus 1. So the zeros that you would actually get if you set that equal to 0 are x equals negative 4 and x equals negative 1. Now we can also find horizontal or oblique asymptotes. So we have some rules here. So if the degree of the numerator is less than the degree of the denominator, then what we say is that our rational function is going to be proper. Okay, so the horizontal asymptote is going to be at y equals 0. But if the degrees are the same, okay, so the degree of the numerator is the same as the degree of the denominator, then y is going to be equal to the coefficient of the first term in the numerator divided by the coefficient of the first term in the denominator, and that is going to give you your horizontal asymptote. And then if the degree of the numerator is larger than the degree of the denominator, then you have to either do long division or synthetic division in order to find your oblique asymptote if one exists. So let's look at this example here. We have r of x equals x minus 12 over 4x squared plus x plus 1. you'll notice the degree of the numerator is 1 and the degree of the denominator is 2. So that means that our function is proper because we have a smaller degree in our numerator than we do in our denominator. So that means y equals 0 is going to be our horizontal asymptote. Now if we look at this one, we have r of x equals 8x squared minus x plus 2 over 4x squared minus 1. You should note for this one that the degree of the numerator and the degree of the denominator are actually both the same. The degrees are both 2. So all we have to do is look at these coefficients. So we're going to end up with y equals something as our horizontal asymptote. And all we have to do is we take the coefficient of our numerator, which is 8, and divide it by the coefficient of the denominator. These are both on the leading terms, okay? So we get 8 divided by 4, which just gives us y equals 2. Now, please make sure when you're writing your equations for your horizontal asymptotes, if it's asking for an equation, you need to put y equals. Same thing with vertical, you should have x equals. Now, if we have something like this, where we have a horizontal or an oblique asymptote, we can take a look at something like this, where we have 3x to the 4th minus x squared over x cubed minus x squared plus 1. So for this one, the degree of the numerator is larger than the degree of the denominator. So what we actually need to do is we need to use long division, okay? And I'm not going to go through this entire step, but this is explained in your textbook. I believe it's also explained in a review section, which is probably worth looking at. You can also Google how to do long division of polynomials, which would be pretty helpful as well. So if you actually do this, all you care about is kind of this entire part here, which is just going to be 3x plus 3. So that means that our graph is going to have an oblique asymptote. The equation of that oblique asymptote would just be y equals 3x plus 3. Now, if we take a look at this one right here, we have 2x to the 5th minus x cubed plus 2 over x cubed minus 1. If we go ahead and do some long division there, we have this equation that kind of emerges, which is 2x squared minus 1. So what we can actually say is that for large values of x, our graph is going to approach y equals 2x squared minus 1. Now that's going to be a parabola. It's not a linear function, which means that it's not actually an oblique asymptote. It will still be approached. It's still kind of important that you draw this on your graph so that you see what your graph might look like in the end, but there's not actually a horizontal or an oblique asymptote there. The horizontal and oblique asymptotes are just going to happen when basically your numerator and denominator, for this one in particular, the numerator's degree is 2 larger than the denominator's degree, and that's going to basically force this to be an x squared term. So that means that you're not going to have any oblique or horizontal asymptotes. So we have a summary here, okay, and this is given in your textbook, which I would suggest definitely reading, but these are just the same things that we had gone through, okay? So if n is less than m, meaning the degree of the numerator is less than the degree of the denominator, then y equals 0 is going to be your horizontal asymptote. If n is equal to m, then all you have to do is divide the two leading coefficients to get your horizontal asymptote. If the degree of your numerator is 1 larger than the degree of the denominator, then the quotient that you obtain by going ahead and doing some long division is going to be your oblique asymptote. And if the degree of the numerator is 2 or more greater than the degree of the denominator, which was like the last one that we just did, then the quotient that's obtained is not going to be either a horizontal or an oblique asymptote. Your graph will approach the equation of that parabola or whatever it is that you're talking about, but it's not actually going to be an asymptote. So section 5.3 talks about the graph of a rational function. So there are several steps that we need to take in order to be able to actually look at a graph of a function and to be able to graph it. So it's really important that you're comfortable with these steps. Typically in my math lab, they're going to kind of guide you through it by asking you question by question, but you do need to know how to find each of them, okay? So the first step, and we're going to just go through this in an example, okay? That's kind of the easiest way to do it, is to actually factor the numerator and the denominator and then find the domain. Okay, so if we have this rational function here, we have r of x equals x minus 1 over x squared minus 4. We're going to factor the denominator and the numerator. Numerator we can't do anything with, but denominator factors into x plus 2 times x minus 2. And then we always find the domain before we cancel anything. So no canceling of anything yet. And what you should do to find your domain is set your denominator not equal to 0. And what you'll find is that you get x not equal to -2 and x not equal to 2. Those are kind of the 2 points that cause issues. So your domain can be written as x such that x is not equal to -2 and x is not equal to 2. Now step 2 is to write r in lowest terms. There aren't any common factors in our case between the numerator and the denominator, so it's already in lowest terms, so we don't need to really do anything there. Step 3 is to go ahead and locate the intercepts on the graph and then determine the behavior of r near each x-intercept using the exact same procedure as for the polynomial. So if we actually plug 0 in for x, so we plug 0 in for our x's here, what we're going to end up with y is 0 minus 1, which is just -1, over 0 squared minus 4, which is just -4. -1 over -4 just gives you positive 1/4, so that is going to be your y-intercept. And then the x-intercepts we find by setting y equal to 0, which is equivalent to just setting your numerator equal to 0. So if we set our numerator equal to 0, we have x minus 1 equals 0, so we get x equals 1 as the only x-intercept. And I'm going to skip this part where we find the behavior near the 0 as it's not as important. Step 4 is to locate the vertical asymptotes. Now, if you recall, vertical asymptotes happen when your denominator is 0. So if we set our denominator equal to 0, we get 2 vertical asymptotes, x equals -2 and x equals +2. The horizontal asymptotes, if you look at the degree of the numerator, the degree is 1. The degree of the denominator is 2, which tells you that y equals 0 is going to be our horizontal asymptote. So at this point, we have asymptote at x equals -2, asymptote at x equals 2, asymptote at y equals 0, and then we have 2 intercepts here. We have 1, 0, and 0, 1/4. So what we want to do is we want to actually use those zeros of the numerator and the denominator. So we want to use our vertical asymptotes of -2 and 2 and our x-intercept of 1 in order to go ahead and find that. So we kind of group these into intervals, all right? So we have from -infinity up to -2, from -2 to 1, from 1 to 2, and then from 2 to infinity. And then we just pick a number in each of those intervals. So you want to pick the nicest number you can. So -3 is a pretty nice number in this first interval. 0, we're stuck with a fraction for this one, so 3/2, and then 3. And then all we need to do is just plug this value that we chose into our original equation. And for each one, this I would leave to you guys to do, but you would plug -3 in and you'd get -0.8 out. You'd plug 0 in, you'd get 1/4 out. Plug 3/2 in, get -2/7, and plug 3 in, you'd get 0.4. So since this number is negative, that means that we're going to be below our x-axis. Since this one's positive, we're going to be above our x-axis on this interval. We're going to be below our x-axis on the interval from 1 to 2, and above our x-axis on the interval from 2 to infinity. So if we take all of this and put it all together, what we should see is that we actually end up with something that looks like this. So we're below our x-axis from -infinity up to -2. We're above our x-axis from -2 up to 0, or sorry, -2 up to 1. And then we go below our x-axis from 1 to 2, and above our x-axis from 2 to infinity. Now, I would highly recommend that you always pick a couple of extra points, make sure that your graph is looking correct. It doesn't take too long to pick extra points to kind of see and make sure that your graph is indeed correct. But the most important things to kind of start out your graph correctly are going to be to plot your asymptotes correctly and plot your intercepts correctly, and then figure out where your graph is above and below your x-axis.